Okay, so this video is still on linear dependence, basis and dimension of spaces, and we are going to describe geometrically the linear dependence of two vectors. So suppose we are in R2, so let us say this is the x-axis and y-axis. We say that two vectors, vector u and vector v, we say they are linearly dependent on R2 if and only if they lie on the same line through the origin. Do not forget this. Okay, so two vectors, let's suppose one vector like this and another one like this. So in R2, if two vectors, or it can be a vector like this and another one like this, two vectors that so this could be u and all this could be v. Okay, two vectors on R2, if they lie on the same line through the origin, okay, we say that they are linearly dependent. So from the geometric point of view, what about R3? Let us say we have x here, y and z. When are two vectors linearly dependent? Let us say we have a plane alpha and that plane crosses the origin. Okay, so we say that three vectors u, v and w, they are dependent if and only if they lie on the same plane through the origin. Let us say this, so this is plane alpha, three vectors will be linearly dependent if they lie on the same plane that crosses the origin. Okay, let us say the equation for this plane is, I don't know, x plus y plus z equals 0. So vector 0, 0, 0 is here, right? Okay, so the plane crosses the origin. So any three vectors, let us say three vectors here, 1, minus 1, 0, minus 1, 1, 0, 1, 0, minus 1. So any three vectors, any set of three vectors that lay on this alpha plane, they will always be dependent. So this is if and only if. Okay, if you have three vectors on the plane, they will be linearly dependent, and they will be linearly dependent if and only if they lie on the same plane. Okay, so we keep seeing some properties of sets of linear dependent and independent vectors. If a set is dependent, then any rearrangement of vectors is also dependent. So if we have a set of vectors like this one, v1, v2, v3, vm, if we rearrange the vectors, and if this set is dependent, if we rearrange the vectors, it will still be a dependent set of vectors. So this means that any other set of vectors, like vi1, vi2, or rearrangement of the same vectors, okay, well, I have to stop at m, right, v, because I have to have the same number of vectors here. So this is a rearrangement of this set. Okay, if this one is dependent, then this one will also be dependent. The proof is simple. Let us say that v1 v2, vm, so these vectors, let us say that they are dependent. Okay, so if they are dependent, that means that we have v1 plus v2 plus v, what was the letter I used, m, that will be 0, with the scalars here, a1, a2, etc., am. Okay, so if they are dependent, this addition will be 0 without all these scalars to be 0. Okay, so any number of these can be non-zero and we will get 0, so the set is dependent. Okay, so but if this happens, then if I rearrange the vectors, like here, vi1 plus vi2, etc., plus vim, if I rearrange them, and if I rearrange them with the scalars ai1, ai2, aim, I will also get 0, where not all of these scalars will be 0. Okay, so I don't know where did I stop here. Okay, not being 0. Okay, I'm going to put j here because I cannot put aim because they cannot be all 0. Okay, so there will be a subset, okay, that will not be 0 and the others will be 0. Okay, so this set here is also dependent. Okay, now if we say if a set is dependent, then any rearrangement of vectors is also dependent. We can say that if a set is, I'm going to write it, independent, okay, then any rearrangement of vectors is also independent. Okay, and the proof is the same, of course.